welcome Dr. and invite him to deliver his session. Sir, please, sir, hand over to you.
Yeah, thank you. Good afternoon, all. I hope all the participants have joined, right? Okay.
Yes, sir. Yes, sir. Some of them are joining.
Right.
Yeah.
Yeah, my screen is visible?
Yes, sir. Yes, sir. Visible.
Visible, right. Okay.
Yeah.
In presentation mode. Fine.
Okay, sir.
Right. Okay, thank you. So today I'm just trying to discuss the basics. Actually, I consider this not an advanced level topic. Some of the applications that you can use, that is the geospatial tools, specifically GIS. I'm not focusing much on remote sensing. So GIS in hydrology and water resource engineering. So now, before getting into the actual topic, let us look into what are all the global water challenges that we are facing today. So we know that our population is ever increasing, and again, access to the clean water is not there for everyone. That is specifically people living in developing and underdeveloped nations. There is actually ever increasing water demand, and you can see that the map shown here. Most of the developed countries like your northern part of America and Europe, etc., they don't have water scarcity. But when we look at the Asian regions and also Latin American region, you can see that there are so many issues like, say, for example, if we see the entire Africa, you can find that there is always water scarcity. And again, we can divide this water scarcity into two categories. One is physical water scarcity. That means actually you don't have water available. Okay, so water availability itself is less. Then you have economic water scarcity. That means water is available, but then it is difficult for the population to access because of their poor economy. Okay, so as we know that there is an increasing water demand, basically for drinking water and as well as for agriculture, right? Then second thing is too much water. Like you may recollect that we have some floodings which happened in last, say, maybe some 2018 2019 floods. Nobody can forget that. So we have flood hazards that are happening everywhere, not only in India. It is happening in both developed countries and developing world. Okay, right. That is again a problem for us. Then occurrence of drought. We can say that you get excess water in one season and too little in other season. So therefore, what happens? This erratic distribution of the rainfall. Like throughout the year, you may not get the rainfall. You may get the rainfall between, as far as we are concerned, we may get between June to September. Then after that, once the rain stops, then continuously you don't have any rain for next 9 months. Sometimes you may get summer rains, otherwise no. And then most of our region like Kerala, if you see, during the months of April, May, there is drought. Okay, and in some regions, you can see that extended droughts. Okay, so you may have some flash droughts and extended drought period. So those things are again a problem. And we know that whenever you don't have surface water, we may tend to use the groundwater, and due to that, the groundwater levels are going down. Again, that reduced groundwater level is causing other issues like land subsidence, etc. So that is one more issue that we are facing as far as water is concerned, groundwater depletion. But then groundwater depletion actually creates land subsidence, saltwater intrusion. Okay, so such type of things. Then another problem that we are actually going or facing and we are expected to face is climate change impacts. So what is this climate change impact? Like we know that we are emitting these greenhouse gases from the industrial revolution. If we started, we know that the amount of greenhouse gases that are available in the atmosphere is increasing, and due to this, the Earth's surface temperature increases gradually, and this increase in temperature will cause change in our long-term weather patterns. So these long-term weather patterns get affected, and it may lead to something like intense rainfall events and also prolonged drought events. So these are all some of the challenges that we are facing today. Right. Now, by this time, you know that what is GIS and what are the GIS components, etc. Now, GIS basically you use whenever there is a spatial analysis required. Okay, if you are only doing analysis non-spatially, then you don't require GIS, right? Okay. Now, you see the watershed that I have presented on the screen. You can see that the water movement, hydrology is basically you're trying to study the movement of water on the surface, subsurface, and the atmosphere. Okay. So now this water movement is spatially distributed, right? Okay. Then again, how quick the water moves, it is dependent on the terrain and the vegetation. And the amount of surface water, surface runoff, and how much is the water infiltrated and reaching the groundwater, that is actually based on these three aspects, that is the slope, land use, and the soil. Okay, so again, these three things are spatially varying. That means the slope varies within the watershed, it is not constant. You may have some hilly terrain. You can see here hilly terrains are there, so slope is steeper slopes you can expect. And whenever we are reaching the outlet point like ocean or a large lake, then there almost the terrain gets relatively flat. Okay, so the terrain is varying, and land use type, that means within the watershed you may have forests, agricultural region, urban region, etc. So, and the amount of infiltration happening in these regions will vary. Similarly, if you look at the soil, so you don't have uniform soil throughout the watershed. So the soil texture may vary, and depending on the soil texture, your infiltration rate will vary, right? Okay, so therefore you have you may need to go for spatial analysis. And again, we generally do all these water source planning and management on a watershed basis. Okay, so therefore we need to have all these details, and we need to do the analysis on, or we require spatial data, right? Okay, now what is the role of GIS? Basically, why we need GIS in water source planning or watershed management. Now, this GIS provides a platform for data integration. That means when I said that I want to use so many data sets, spatially varying data sets to be used for my analysis. So that means how do I actually uh, integrate these data sets? That means, for example, in a particular location, I have soil type A, where I have a land use type B and a slope C. Okay. And these three combinations are contributing to some amount of runoff. Okay. So then these spatially varying data has to be integrated. So your GIS provides a platform for integration. And also before the final data that we have, sometimes we may need to pre-process the data. For instance, if I want to get a slope, then I have to do certain analysis using the digital elevation model to derive slope. Okay, so this GIS can be used as a data preprocessor and also for data integration. Then spatial modeling. See, I want to do the analysis spatially, right? See, actually you have temporal variation and spatial variation. So when I want to do the spatial modeling, then I require GIS. Again, these GIS can be used for decision support. For example, let us say that I am a person who is working in disaster management agency. Then let us say that I want to know, I want to evacuate the people from low-lying area, okay, or the area which is likely to get affected by flood. Okay, now say let us say that if you try to say this entire basin is going to get, means you have heavy rainfall, then I have to evacuate, start my evacuation. Then which area to be evacuated first? Which area is likely to flood first? Okay, and where I have to take them, which is safe region. Okay, so those type of decisions I have to make. So this GIS can be used as a decision support tool. Now, again, we know that we can just visualize the results in a spatial format, like which area is inundated, which area is not going to be there. So likewise, your GIS can be used as a tool for data integration, spatial modeling, decision support, and also it supports spatial visualization. So I have just shown some flowchart here where you can understand that your GIS actually, you can see, to manage the spatial data and to process, like there are several data sets are here. Okay, so for that GIS can be used, and data acquisition is maybe through remote sensing or any other ground-based collection systems. Okay, so that can be used here. And then after this, in the GIS environment, you can run the hydrological models. Okay, now the data required to run the hydrological model, that has to be prepared. Okay, so there are certain GIS platforms. For example, you can see that HitGeoHMS, HitGeoRAS, etc., are some of the interfaces developed by proprietary people to generate the required data set, that is your GIS data set, for running these models. Okay, now once you use the model, then you perform the actual hydrological modeling, then you get hydrographs. Okay, so then from that you can use further for analysis. So that is you can prepare this flood hazard maps or flood risk maps, etc. Okay, now let us discuss on some of the spatial data sets that are used for hydrology. So I am just listing only few. There are several things that can be used. Okay, so if you look at these data sets, you can say that you may use DEM. DEM stands for Digital Elevation Model, and those who are already working in hydrology or water resources, you know that that is if you want to represent the topography which is continuously varying, then you use this raster dataset for representing the topography. So each grid cell in the raster data will give you the elevation of that location. Okay. Then land use land cover map, then soil data. You may use rainfall data. Again, rainfall data, you may have point data. Then you have to do the pre-processing in order to get spatially varying rainfall data. Then you also have stream network data, etc. Okay, so these are the data. Apart from that, you are working with groundwater. Then you may have the borehole data, etc. Right. Now, let us start with digital elevation models. Shortly, it is called as DEM. Okay. Now, this is a geospatial model which represents the ground elevation. So that means it is like an image with raster cells which are arranged in rows and columns, and each cell is going to represent the elevation. Okay. Here, DEM is a generic term that we use. But if you are very much specific, then we have two other terminologies that we are actually supposed to use. That is digital surface models and digital terrain models. Okay. Now, what is the difference between digital surface model and digital terrain model? So if you see here on the raster map, if I am trying to get the elevation, now if I try to get the elevation including these buildings and trees, that is the elevation what I am observing is not the actual ground elevation. I am actually observing the elevation of the tree surface or the building. Then that is called as digital surface model. So whenever we are trying to get the DEMs from satellite based observations, for example, your SRTM or your ASTER data sets, then what you are going to get is digital surface model. Okay. But what is DTM? DTM represents the bare earth ground with objects removed. So that means if I remove these objects which are placed on the ground, then what I am going to see is only the actual earth surface. So if I try to get the elevation of the actual earth surface, then that is called as digital terrain model. Okay. So now, if I want the digital terrain model, I have to use LiDAR. If I am using sources such as SRTM DEM or ASTER DEM, what I am going to get is only the digital surface model. Okay. Then, if I am trying to do the ground-based survey and trying to build the contour, okay, then in that case, what I am going to get is my digital terrain model. So that means ground-based surveys, you get digital terrain model by interpolation. And if you use LiDAR, you can get, especially when you have vegetations, not on buildings, but wherever you have vegetations, it is possible for you to get the actual terrain. Okay. But if it is urban area, then even LiDAR, it is not possible. Only thing is you have to use ground-based survey and you have to remove the buildings. Okay. Now, resolution. So whenever we are using these DSMs or DTMs for a specific application, okay, again, I am telling you this DSMs, when we use it for something like if you want to delineate the watershed, then DSMs are fine. But if you are working for flood inundation mapping, then DSMs are not going to work. You may need to have DTMs, because if whatever you are getting is tree canopy. Okay. Now tree canopy is there is a deviation of maybe 3 to 4 meters from the actual ground and the canopy surface. So the flood inundation, whatever you are going to get, may not be the true representation. Okay. So now when we are looking at the resolutions, again, if you are working on, say, a watershed level, then 30-meter DEM or 90-meter DEM is well and good. But if I am working at urban flooding or say that floodplain inundation separately, if I want to work, then I may need to go for high resolution DEM. Okay, so now what is the difference? You can see here. Now this is the contour map that all the civil engineers are quite familiar with. Okay, so that you have each contour representing the elevation of that. Now if I try to interpolate this contour, okay, then what I am going to get is something like this. Okay, so this is the raster data. So here you can see that if you zoom in, you can see some square pixels. Okay, so each pixel is representing elevation. For example, in this case, you can see that this blue colored one is representing 0 elevation, whereas the bright, okay, that is representing higher elevation. Okay, sorry, it is actually slope. In fact, I have just shown the slope map here. So here, this is derived from DEM. Okay, so here you can say that your DEM is also very similar to this, where each pixel is going to represent your elevation value. Okay, so this is again derived from DEM. That I'll just explain you a little later. Okay, then next thing what you can get is land use land cover data. See, for example, this is the Bharatapuzha River Basin, and this is the land use land cover data belonging 2017 year. So why do we actually require this land use land cover data? Because as already mentioned, your hydrology is highly dependent on land use land cover. So that means how much runoff is generated, surface runoff is generated, how much is the amount of water getting infiltrated, and how much is going to the groundwater, etc. All these things are based on your land use land cover. Okay, for instance, if you let us say you have a slopey terrain, and if I have a vegetation in that slopey terrain, then my runoff will reduce. Why? You always know that your velocity of flow is actually dependent on roughness. Okay, as and when the roughness increases, velocity reduces. So this roughness is indeed dependent on the vegetation, right? So depending on the nature of vegetation and whatever is existing in the, or I can say that the land use or land cover types. Okay, for example, in the case of forest, you may have less amount of surface runoff, right? So in the land use land cover map, you can see that you can have different classes, and each class may have its own effect on the amount of runoff generated. Okay. Right. Next one is soil and geology data. Those who have already worked in some water source field, you know that we actually look for soil textural classification, because your infiltration rates are purely dependent on the sand, silt, clay percentage. Okay, how much percentage of sand, silt, clay is present in the soil composition. Okay, so basically you work with soil textural groups, like you group the soil texture into A, B, C, D, where A will give you high amount of infiltration, and D will be having very less infiltration. So you can see that how we are trying to categorize. Okay, so this region very high infiltration, and you can have reasonably good here. It is poor, and this region you can see that very poor. Okay, so that is if it is clay or sandy clay or clayey loam, I think this you know already. Silty loam, silt, loamy sand, okay, sandy loam. So depending on what percentage of clay and sand are present. So based on this textural grouping, as I already mentioned, you have 4 groups, and based on or these groups indicate different levels of infiltration rates of the soil. Now, apart from this, we also look for geological formations. For instance, see, we may actually wonder, like we have a rainfall about 3000 mm in a year, but then why do we experience this drought, and why our wells are getting dried up during summer? That is, most of the region what we see here is made up of laterite. That is the geological formation that we have. Now, these laterites are porous in nature, and then because of that, even though you have adequate groundwater recharge during rainy season, since the laterite is porous in nature, you have all these flows that are actually converted into subsurface flows and reaching the nearby water body. Okay. So, therefore, you require to have this soil textural data and then the geological formations. Basically, you call that as lithology, litholog that we'll take in order to understand this. Okay, and it also basically, if you want to do this groundwater flow modeling, okay, so then you require this geological formation data. Okay, right. Then next thing is we require hydrometeorological data. So you know that in a hydrological model, the forcing input is rainfall. So rainfall, location of the rainfall stations and the rainfall data, and the temperature. Okay, temperature and evaporation. All these things, see, we know that the rainfall is not actually occurring in one location. It is falling over the entire surface of the watershed. But then the measurements what we take is on only at specific locations, right? We don't measure at all the throughout the watershed. We are not measuring. Okay, we are measuring only at some specific locations. Okay, so therefore, what I'm trying to say is these are all the representative points. Okay, these are the representative points where you are trying to measure the data, and we need to do pre-processing in order to get the spatially distributed rainfall, temperature, evaporation, etc. Right. Then, as we know that we are using GIS data, and how do we actually get the GIS data? For example, land use land cover map. So we generally use, because this land use land cover map, if I say it is dynamic in nature, like the land use land cover of say 2000 and 2010, if I take, there will be a lot of difference. Whereas your soil and topography remains more or less constant. Unless the topography may change if there is any change in your, for example, landslides or something that human is intervening and trying to cut the like quarrying or something like that. Otherwise, mostly the topography will not change. Okay, but land use land cover changes with seasons and from one year to the other year, etc. Okay, so in order to get this land use land cover map, we may use remote sensing data sets like we have satellites like Landsat satellite, series of satellites are available, and then IRS satellites. Now we have Sentinel, MODIS, etc. Okay, so depending on at what resolution we are trying to use the data, we can go for any of the satellites, and you can apply some classification technique in order to derive this land use land cover. Okay, so this remote sensing data, you try to use some classification algorithm, then you get a thematic map that is land use land cover. So this becomes a GIS data. Right. Now we will move on to the watershed analysis. Okay. Right. Now, what is a watershed? Watershed is an area of land where all the water flow falling on or flowing beneath, it drains to single outlet or a common water body. Okay, it may be stream, river, lake, or ocean. Okay, so that is a watershed. So we actually, as a water resource planners, we actually do any management or any planning only at watershed level. We don't take political boundaries. Okay, whether it belongs to say Kozhikode district or Malappuram district, that is immaterial for us. We actually has to, or we should do all our planning only on watershed basis. Okay, so this watershed don't know whether it is part of this district or the other district, right? Then what is drainage divide? Watersheds are separated by high points in the landscape, such as mountains and ridges or hills. So these are called as drainage divide. So if you see here, I can just show you a picture. So now you see, so this is your watershed divide. So this is basically a ridge line. Okay, so where the water falling this side of the ridge will actually reach here, and the other side of the ridge will be part of other watershed. So people from this Kozhikode and Malappuram, you may understand easily that and also Wayanad. We have like Kuruvadi, that you maybe it's a tourist spot that you know, and the water falling in that region, you know that it is part of Kaveri River. Okay, that is actually a Kabini, and you also know that we have these Banasara Sagar, everything constructed. Actually, that watershed, what we are trying to see, that is a Kabini watershed. And Kabini watershed is on the other side of the ridge. That is in the Western Ghats, it is on the other side of the ridge. So therefore, the whatever is the water falling there will move towards the eastern part. Okay, it is not west flowing. So it moves towards the eastern part, enters Karnataka, then gradually moves towards Tamil Nadu, and finally drains in Bay of Bengal. Okay, so the ridge, if it is falling this side of the ridge, then it may be part of Chaliyar. Okay, so therefore, whatever is the water, actually you can say that both surface, that is, these are the surface water, and subsurface water, that is the groundwater. everything should drain to one single outlet. So then you call it as, that unit is called as watershed. Okay. So we actually do the analysis on watershed basis, right? So therefore, my first task is how to actually get the watershed area. Okay, so that is my first task. So I'll just explain you how do we actually delineate the watershed using the DEM. So DEM is nothing but, as I already mentioned, is a digital elevation model which represents the elevation of each location, the watershed, right? So from the DEM, what we do is we try to derive flow directions. Okay, so the simple way is flow direction and further you move here. But then before that, what we need to know is we need to understand whether there are sinks in my DEM. See, in your watershed, there may be something like a water body like a lake is there. Okay, so lake is a depressed portion within the watershed. Now, suppose the water is flowing and naturally from every direction, the water will flow towards the depressed point or the depressed location to the lake. But then once the lake is filled up, again it has to take the next lowest point, right? So therefore, what we are trying to do is we are trying to fill this in order to get the actual flow path or the flow direction. So first thing is you actually create a DEM which is called as depressionless DEM. Okay, so you have to have a separate thing like filling this DEM. So if you, I think I can just show you this. Okay, so now you can see that this is a DEM where these colors are representing different elevation. Now you can say that these dark brown colors are elevated compared to this light brown. So now if you see here, this circle, there are some pixels which are surrounded by dark brown color. Okay, so that means these two pixels are surrounded by the pixels with higher elevation. So that means this is a sink. Okay, so in order to have a proper flow path, what I have to do is I have to remove this sink. So in the right side, you can see that that sink is removed. So what I will do is I will fill this sink with the same elevation as that of the surrounding pixels elevation. So that sink can be removed. So this is the first stage that I'll going to do in my analysis. Okay, so that is I'll be ending up with depressionless DEM. So using this depressionless DEM, then I will be doing a process which is called as, that is, I may get flow directions. Okay, once the depression, okay, so now from this DEM flow direction, say let us say this is a raster image that I have. Okay, now I want to identify in which direction the flow is going to happen. Okay, for example, let us say this first cell 78. Okay, so this is the elevation of this cell. Now from this cell, whether you can see that this is 74, 72, 67. Okay, so from this the flow can happen in any of these three cells. So how to decide in which direction the flow is going to happen? So it is very obvious to you that why the flow is happening. First of all, why the flow is happening on the ground? It is due to the gravity, right? So surface flows are due to the gravity. So when there is a difference in elevation, then that creates slope, right? Spatially, if there is a difference in elevation, that creates a gradient, right? So wherever the gradient is steeper, only in that direction the flow is going to happen. Okay, so so if I take these three, you can always calculate what is the steepest gradient. For example, here the elevation difference is 4 units. Here the elevation difference is 6 units. Okay, here it is further more. Now, how to calculate your gradient? The difference in elevation divided by the center to center distance of the pixel. Okay, so for example, in this case, let us say that my this pixel size is 10 meter by 10 meter, 10 by 10 meter by 10 meter. Then here in this direction, the slope will be 6 by 10. In this direction, it is 4 by 10. And in this direction, you can say that it is 11 by square root 2 into 10. So that means 1.414 times 10, right? Because this is the diagonal distance. Okay, center to center means it's diagonal. So you have to take the diagonal distance. So from that, you can understand that this is the steepest gradient. So therefore, the direction will be like this. Okay, so you can see that the flow direction. Okay, but then in the system, it is not possible for us to indicate it by arrow. Rather, you know that the computers will actually recognize everything as numbers. So for each direction, basically we try to assign numbers. For example, this may be different for different software. I am not saying that this is the universal standard. Sometimes they start one from the north and they progress. Sometimes they start one from the right, that is east. So starting from east, if I say this is 2 power 0, 2 power 1, 2 power 2, 2 power 3, etc., 2 power 7. Okay. So whenever the flow is happening towards east, then I may mark it as 1. If it is going towards southeast, then I may mark it as 2. So here the direction from here is towards southeast. So I am marking it as 2. Okay, so you can see the actual direction is this direction. Okay, so likewise, you can check for any of these things. So for example, if I say this pixel, okay, it is 55. Now, surrounding pixel, if I take, I can say that 20, the possibilities are 22 and 21, right? But if you calculate the gradient, because this is diagonal and this is the distance is only 10 meters center to center, basically this will be the steepest gradient. So therefore, you can see here it is indicated as 1. So that means the direction of flow is in this direction. Okay, so the algorithm here, what we use called as D8 algorithm, that is you are trying to have 8 directions. So from any pixel, the flow can happen in any of these 8 directions. And you can say that only in one direction the flow can happen. Okay, suppose for example, you have there are many pixels which are having values less than 55. But then only in one direction the flow is happening, that is the steepest direction. Okay, so it is therefore it is called a single path, right? Now, as I already mentioned, you apply this flow direction algorithm, D8 algorithm, and then you can get this final flow direction raster. You can see here for each pixel the direction of flow is indicated. So it is indicated by 2 power 0, 2 power 1 up to 2 power 7. Okay, so for all 8 directions. Right. Now, next one is flow accumulation. See, based on the flow direction, I can actually calculate how much flow is accumulated over each pixel. For example, let us move on to the previous case. Okay, now if I take this pixel, you can say that one upstream pixel is contributing. Okay, so that means the flow accumulation for this flow accumulation value for this pixel is 1. But as far as this pixel is concerned, there is no flows coming to this pixel from any other pixel, so it is 0. Similarly, this is also 0. Okay, now if I take this pixel, okay, let us say this pixel if I take, then if I want to calculate what is flow accumulation, what are all the upstream pixels which are going to contribute? Okay, now let us just try to see that. Here I can see for this pixel, this is contributing, and this is contributing. And now if you see this one, it is flowing here and ultimately flowing here. So this is also contributing. And as far as this is concerned, it is flowing here and further flows here. So this is contributing. So now if I consider for this pixel, my flow accumulation value will be 5. Okay, so this is how it is being calculated. Now if I take this pixel, okay, here again, okay, sorry, here one few more things are there. See, like this is also flowing here, right? Okay, this. So it is not 5. So now if I count any other thing, okay, 1, 2, 3, 4, 5, 6, 7. So flow accumulation value is 7 here. Okay, now if I just move further downward, this one. Okay, now this is contributing. This is contributing. This is contributing. This is contributing. This, and this one, this, fine. So all these pixels are actually flowing here. Okay, so if you count this, so 4, 8, 12 plus 6, 18 plus 20. So this will be, flow accumulation value will be 20. Okay, right? So likewise, I can get the flow accumulation. So now just you can see here. So that means from here, if I try to move the downward direction along the stream, so here the flow accumulation will be maximum, and when I just move towards the upstream, it reduces. Okay, so it is indicated, you can see here. So light blue means very low accumulation, dark blue indicates higher accumulation. So now from this itself you can understand, wherever you have more accumulation, that is going to form your drainage. Okay, so now I have just used a threshold. Say for example, the flow accumulation value is 0 to 1394. Let us say I'm just keeping a value of 500. Okay, and any value below 500 I am removing, only I am retaining the value above 500. So all these pixels are having flow accumulation value more than 500. Now these pixels, if I try to digitize or if I try to convert into vector, then this will be my drainage. Okay, now next thing is I want to identify the watershed boundary. So now what I need is I want to specify the outlet points, or you call it as pour points. So here I am just specifying outlet 1, 2, 3, 4, and 5 outlets. And for these 5 outlets, I need to get the watershed. So if this is the outlet, this drainage, whatever is the area that is draining to this outlet should be marked as my watershed for this outlet. Okay. So using that, if I try to mark the watershed, you can see here for this outlet, this thing. So these are the delineated streams. Obviously, these are some errors that we have to process. Okay, because you may have very flat region here, so that may cause such type of errors. Okay, so this is going to be my watershed. Okay, for this outlet, this is the watershed, and for this outlet, this is the contributing area, or this is the watershed. So you can see here. Okay, so we have got 5 outlet points. So for each of the 5 outlet points, what are the contributing upstream area that we have delineated. Okay, so this is how actually you delineate the watershed. Next thing is Strackler stream order. Actually, this is very simple, like which will be very much useful in your morphometric analysis of the watershed. Okay, so it is, we try to understand the hierarchy, okay, and complexity of the streams using this stream ordering. So it is very simple, like this is the part where your stream starts. So those streams are called as first order streams. Okay, now when 2 first order streams meet, then it forms second order stream. Okay, so here also you can see that 2 first order streams, when they meet, they become second order. Okay, now when 2 second order meets, then that becomes third order. Okay, so that means if you have the streams with equal order, they are meeting, then it becomes, from that junction point onwards, it becomes higher order stream. Okay, now suppose a first order stream is meeting a third order stream, then the maximum order is 3, so that continues. Okay, only when equal order stream meets, then from that point, the downward stream, it becomes next order. Okay, when you have unequal order meeting, then the maximum order, that continues. Okay, so you can see here 2 third order streams are meeting, becomes fourth order. Okay, suppose I have some second order stream meeting here, or second order stream meeting here. Still it will be fourth order, it will be third order. Okay, so basically it is used to understand the morphometric and other characters of the watershed. So now morphometric analysis, if we do, we actually try to compute some of the details such as drainage density, stream frequency, bifurcation ratio, etc. Now, in what way they are actually related to hydrology? Right? See, the stream density and the drainage pattern basically represents the subsurface geology, or you can say that the geology of the terrain. Okay. See, for instance, if my terrain is a granitic terrain, okay, in that case, I can expect very high drainage density, because in a granite, you don't have deep percolation. Okay, so therefore, once your topsoil is getting saturated, then the remaining water or the remaining rainfall is going to get converted into runoff. So therefore, the drainage density will be very high. Okay, so you can understand the nature of the bedrock by actually computing the drainage density. Okay, and again, the stream frequency is also one more indicator that will give you how much is the infiltration occurring in the region. Okay, so you can see that total number of stream segments of all orders within a basin divided by basin's total area. Okay, so whether, see, some basins, very large basins, may have only fourth order stream, but sometimes smaller basins will end up with sixth order streams. Okay, right. Then you have bifurcation ratio. See, actually, this also gives you some basic understanding of what will be the flow, etc., that will happen in these drainages. Okay, so it evaluates how drainage network branches by comparing the number of streams of one order to the number of streams in the next highest order. Okay, so these are the some of the morphometric analysis that we carry out in the watershed. Okay. So now moving on, so that means these are all the things that actually indicates the nature of the watershed, basically, which is very much important in the hydrology. Right, now moving on, as I already pointed out, your precipitation. So these are all carried out at specific locations, and if I wanted to have the precipitation over the entire area, okay, so then I have to do certain analysis, that is pre-processing. So if you want to know the spatial variability in the hydrological unit, so you have to calculate the average precipitation. Let us say you want to prepare isohydral maps, you need to prepare depth, area, duration curves. So I'm just going to discuss how this GIS is going to help you in this. So let us say this is the precipitation data. Now this blue colored line is your watershed boundary. Okay, and you have several points where your precipitation is being measured, and you know that there is a large variation. You can see here. Here the let us say unit is mm. So here it is 18. Here it is 35. So you may see that there is very large variation, right? And you have point data. Now the usual process is, in order to get the average of this particular, then what I will do is prepare the Thiessen polygons. So you can see that Thiessen polygons preparation that you know in GIS, you can easily prepare these Thiessen polygons, and this area to the total area of the watershed will become the weight associated to this rain gauge. Okay, so this is how you actually get the representation. That means let us say this is A1. So your A1 times the precipitation here. Okay, so the 742 is the actual area that you can find into precipitation, plus 703, that is the area to into the precipitation, so on, divided by the total area will give me the average precipitation of the watershed. Right. Now the other way is, I can actually do something called as spatial interpolation. So there are several interpolation algorithms available, just like inverse distance weighted, and you can use kriging like spline, take the, or you can get the spatially varying precipitation values. So you see here, these are the precipitation locations with the values. Okay, and if you say that this is the mm that I already mentioned, so you can see that it is varying, right? Within the watershed, it is varying, right? And it is a raster data. So you can prepare, next stage is preparation of isohydral maps. People who are working in hydrology, they easily understand what is an isohydral map. It is nothing but imaginary lines joining equal depth of rainfall. Okay, so like similar to your contours. Contour, it is your say topography, like elevation, lines joining same elevation, you call it as contour, where iso height is lines joining rainfall of same depth. Okay, so you take any duration, and let us say here I have taken 6 hour duration. And for 6 hour duration rainfall, I prepared the iso heights. Okay, right now my next requirement is to calculate the depth area duration. Okay, so duration is 6 hours that I have already fixed. Now for this particular duration, I am going to calculate the depth and the area. So here you can see that this particular polygon, okay, it is just I have converted into polygons. So now I can say that this particular area, I am going to get a rainfall of, okay, I have just written as cm, you can take it as mm. So this much mm. Okay, and again, for if I take this particular area, the average depth I want to calculate. Okay, so that means the average depth will be depth of rainfall into A1 plus depth of rainfall into this area, that is, let us say it is A2, divided by sigma A, that is my A1 plus A2. So that will give me the average depth over the entire region here. Okay, now when I move outside further, that will be A1 into this rainfall, A2 into the rainfall over this region, A3 into rainfall over this region, divided by A1 plus A2 plus A3. So like that. So now, if I want to do this computation, first of all, I need to have the area, right? Area of these polygons. So from the isoidal map, I can actually, what I can do is I can just convert that into polygons, and for each polygon, you can say that polygon, I've given some IDs, and each polygons, I can get the area. So here, polygons with same amount of rainfall, the IDs are same. Okay, you can see here. That is, so therefore, I can actually prepare the depth, area, duration curve. Okay, so how much depth, how much area, right? Okay, now moving on and hydrologic modeling, right? So generally, for any hydrological modeling purpose we require spatial data sets like rainfall, soil, land use, topography, and then time series data. Time series data sets, we can say that discharge. Okay, so you can say the temporal data set, time series can say temporal and use spatial. But again, rainfall is actually considered as spatio-temporal. That means it is going to vary spatially and also temporally. So that means if we take rainfall, it will be a spatio-temporal variation, right? Okay. Then actually, again, this is one more issue, like how do we actually account this temporal variation? That is depending on what type of model you are going to use. So based on that, you may actually see whether you're using a temporally distributed rainfall, or sorry, spatially distributed rainfall, or you are just using one rainfall, average rainfall with temporal distribution. So it depends on the model type. Okay. So anyhow, so using this, you can use hydrological models which can be semi-distributed or distributed. Then use that for model calibration and validation, and further you can use it for forecasting or whatever your requirements are. Okay, for any type of rainfall forcing. Okay, so this discharge data sets may be used for calibrating and validating the models. Okay. Now, simple runoff computation. Basically, any of the water source student might be knowing this simple technique, that is curve number technique. Okay, in order to calculate the runoff depth. So the GIS inputs used for the calculation of curve number or ultimately runoff is land use, land cover, hydrological soil group, and precipitation. Okay, now the basic equation, your runoff depth is nothing but precipitation minus abstraction, okay, by square by, this is basically the equation derivation I am not going to use. You can understand. Precipitation minus loss in the form of abstraction, that is initial abstraction, and infiltration, that is going to be your runoff. Okay, now here S is nothing but how much moisture your soil can retain, that is potential soil moisture retention. Okay, now this how much moisture your soil can retain, basically it is function of curve number. Okay, now this curve number is derived from two things, that is your land use, land cover plus hydrological soil group. Say for example, my land use, land cover is urban. Okay, then my curve number will become 90 plus, or let us say 94 or something like that. Then that means very minimal retention is there for my soil. That means my soil moisture retention is minimum. Most of the thing is converted into runoff. Okay, if suppose my land use, land cover is, say for example, grass, fully covered grass, and my soil type is, say for example, it is sandy loam. Okay, so that means your I think soil texture classification we have seen. So let us say it is group C. Okay, so in that case you may see that it is not very poor. Okay, so group A is very good, right? Group B is moderate. It is then group C is again it is poor, and group D is very poor. Okay, so like that you have this hydrological soil groups. So now for this soil group particularly, let us say group B in combined with your grass. Okay, so then in that case my curve number will be somewhere around 48 or around 52. Okay, so now that means more amount of moisture can be retained in the soil and very less amount of runoff is generated. Okay, so in that case my CN will be somewhere around, as I already mentioned, 48 or somewhere around 50, somewhere 55, something like that. Okay, so this is how you actually compute. Now, how do we use GIS? Okay, so let us say that I have land use, land cover map. So there are three land use, land covers. Okay, you can give any name. For example, this is forest, agriculture, urban. Okay, now you have soil groups ABC. Okay, hydrological soil group A, soil group B, soil group C. Right? Okay, now if I try to overlay these two things, now I will get a particular area here. Let us say I am just trying to Okay, so let us say this area. Okay, so this area basically it comprises of soil group C and your land use 2. Land use 2, we have taken it as agriculture, right? This agriculture and this is forest. Okay, this is urban. So now this region, what I have marked here, okay, so this region, this is actually a polygon which has your C is the soil type, agriculture is the land use type. So for agriculture and the land use type C, what is your curve number? That I can get. Okay, so that means from the curve number, I can actually use that. So from the curve number, I can calculate what is S. Okay, and once S is computed, I can get what is my runoff depth from that particular polygon. Okay, how much runoff is going to get generated from this polygon. Same way, I can get for each of these polygons. So I can easily say that how many are there? 1, 2, 3, 4, 5, 6 polygons are there. So for all these 6 polygons, what is the or how much is my runoff generated, that I can get. Okay, so you can Q. Okay, so for each polygon I can calculate. Okay, so now you can see here, using that I can basically map the a simple process that you can understand. So from the, as we have discussed so many things now, so from the satellite data, that is IRS satellite data has been used, and you can calculate the, get the land use land cover map. Okay, so then from soil data, soil texture and hydrological soil group, that is A, B, C, D, whatever it is, right? Then from these two things, as we have already done here, okay, land use land cover over soil, you get this spatial overlay, right? And then from the rainfall data, okay, you have this CN, and you know, I think those who are know much detail about SCS curve number or NRCS curve number, you know what is AMC condition. So I am not going to discuss on that. So from the rainfall, finally, you build this model. Okay, then you calculate the runoff from each pixel. Okay, then after that, you may need to validate. So here they have used validation based on the groundwater levels. Okay, available groundwater levels they have used. Okay, so but then that will give you the runoff in mm. So how much runoff can be or how much runoff is generated from the watershed can be calculated. Okay, so that is, you can do the runoff potential mapping. Right. Now, why or how it is going to get used, that we will see. Right. And before that, I told you there are something like we need to pre-process certain data to derive our some derived data sets. For example, your slope. Okay. So now, if this is your DEM, now I need to calculate the slope. So how do I calculate the slope? Nothing but dy by dx, yes or no? So this one indicates your y, that is elevation. Okay, now let us say this 3 is your elevation. Okay, now I want to calculate the slope. So I need to just, which direction is steeper, I have to see. And then this minus, say for example, this direction. So 3 minus 1, 2. 2 divided by the center to center distance. So that will give me the slope. Okay. So likewise, I can calculate the slope. Aspect is the direction of the slope. So which direction it is sloping. So you can say that you may have 0 to 360 degrees, and based on which direction the slope is, you may actually give the value either 0. 0 means north. Okay. And then 360 means 90 is your east, 180 is south, 270 is your west, and 360 or again it is 0. Okay. So that will give you the aspect. So these are the things that we may require for certain analysis. Okay, now let us try to understand. We have already seen how to get the slope. Okay, now people may be familiar with this time of concentration. It is nothing but how much time it requires for hydrology, for the raindrop which has fallen on the hydrologically remote point to reach the outlet. Okay, that is called as time of concentration. Okay, so let us say if I take these two catchments, if suppose a rainfall, which is raindrop falling here, may actually enter into any one of these streams on the surface, it has to flow. Okay, and it has to reach the outlet here. Okay, so how much time it takes for the raindrop which is falling at the hydrologically most remote point of the watershed to reach the outlet? That is called as time of concentration. Okay, so you may have different shapes of watershed. See, for example, the left side you call it as fan shaped or broad leaf watershed. Here it is elongated watershed, or you can also call it as fern shaped watershed. So depending on the shape and the topography like slopes, etc., the time of concentration may vary. It is not simply the distance. Okay, so it is basically the slope and other things are also coming into picture, right? So you can see here the TC is nothing but it's an empirical formula. Actually, it is an empirical formula based on watershed lag method given by ACS. Okay, so it is basically function of your flow length. The formula I'm not very much interested in explaining. So this is flow length and how much is the potential retention. Okay, so that is again dependent on the, we have already seen what is that S, our NRCS curve number. Okay, and then average watershed slope. So now you understand that your TC is function of your flow length. S is again, you can say it is curve number. Okay, and curve number is again, it is nothing but your function of your LU plus your soil, right? Soil type. Okay, so that means length is there, soil and land use is there, slope is there. So using all these things only, you are calculating your TC. Is that clear? Okay. So the flow length is basically calculated from the remote location, most remote point. Right. Now we will just look into some of the hydrological models that we are using. You can say that one model commonly used. So there are several models available, but I'm just trying to discuss only some of the commonly used models like SWAT. SWAT is Soil and Water Assessment Tool. Okay, it is used for small watersheds to river basin scale. So any scale it can be applied. And the advantage of this is it is free, and you can use it for surface water modeling and as well as for groundwater modeling. And also it has modules that will support your water quality. Okay, and also you can use it for analyzing the climate change impact, etc. Okay, so that is the SWAT model. And again, you have HEC-HMS. Actually, it is for simulating the hydrological response of a watersheds to precipitation, including runoff, infiltration, channel flow. Okay, so actually these models have certain models have certain advantages. So depending on what we are looking for, okay, we'll be using the models. For example, if I am working on flood modeling, then I'll be working for HMS and HEC-RAS. Whereas if I am working on continuous stream flow models, then I'll be using SWAT. Okay, so it depends what I am interested in. Okay, so basically, if you see here, these are some of the models that we actually use for hydrological models. And again, there is a difference. Like if I see this SWAT, it is basically a semi-distributed model. Okay, whereas your HEC-RAS can be considered as a fully distributed model. Okay, so that is depends on what for we are using. We may choose the models. Okay, now simple example how the SWAT model is being used. You can see the processes that are being modeled in SWAT. So you can see that you may use or see the processes. If you see, you can simulate the runoff process. Okay, for that you have to give the precipitation data, and your crop data is required in order to calculate your evaporation and temperature transpiration losses. Okay, basically you may need further, like temperature is also required. Okay, then it will calculate the infiltration, okay, soil moisture, and Vardhan modeling is there, which will calculate the lateral flow or subsurface flow. Okay, and groundwater module will calculate the return flows. Okay, and also recharge in the deep aquifer. Okay, so now if you see here, the inputs that we generally use is DEM, crop data layer, or sometimes you call it as land use, and soil. Okay, so these are the data sets we generally use. Okay, a delineate watershed, you just give the slope, then you actually bring up this hydrological response units, which are similar units. Okay, so that means you group a certain region and you take the characteristics of those entire region as one single character, like it has same slope and same soil characters, like that you just group. Okay, so HRUs will be defined. Then you try to set up the model, and when you try to run the model, you require certain things like certain parameters that are need to be calibrated, because whatever the parameter required for the model cannot be given, because you cannot measure those things directly. So it requires calibration. So for calibration, you need river discharges so that it can be calibrated, and you have some modules like SWAT cup, which is used for calibrating the model. Okay, and you can get the simulation. So you understand that for this, when you want to run this model, you require spatial data or GIS data. Okay, now moving on to HHMS. I am just trying to put both HHMS and HECRAS together. So you can see that for modeling, HHMS modeling, basically you require GIS data. Okay, so GIS data, your DEM, okay, and also you may need to prepare this. If I have more than one rain gauge station in my watershed, but then I have to prepare the Thyssen polygon, and finally I have to come up with one representative forcing input. Okay, so then that rainfall data has to be given, right? So if it is more than one rain gauge station available, right? So after that, you use the discharge data from flow hydrograph, that is measured one. Then you actually carry out the modeling. Okay, so that is you can use 2D numerical model in order to calculate the flow depth. Okay, then once you get the flow depth, whether you are using it for flood hazard or from the flood hazard, or you going to prepare the flood risk map. Okay, so those things are different. Flood vulnerability, other things that comes later. Okay, so you are whenever you're going to do any hydrologic or hydraulic modeling, you should understand that most of the inputs that you require are spatial inputs, and those spatial inputs are to be pre-processed, which requires GIS. Right now, if you want to prioritize the watershed for watershed management, we all know that erosion is one of the major issues that we face. So erosion, one thing is we lose enormous amount of topsoil, and not only this loss in topsoil is a problem, this soil is being carried out in the streams and finally ending up in reservoirs. Okay, so this, whenever it is ending in the reservoir, the next problem that we face is the useful life of the reservoir. It gets reduced. So you can very well see the data provided by the Kerala Water Authority regarding their reservoir siltation or reservoir sedimentation. Okay, so much of sediments are accumulated in the reservoir because of the upstream erosion. Okay, so now if you want to calculate on an annual basis how much soil is being lost in the watershed, then you may use a simple equation by which is called as universal soil loss equation, and there are revised versions. You have revised USLE, modified USLE, depending on what actually you are using it for. That is fine tuning it. Okay, but then let us look into the basic equation. So this basic equation requires some of these inputs like your rainfall erosivity, soil erodibility, and LS factor, that is slope, length, and steepness. Okay, so these two things are together. Okay, LS factor and crop cover management and conservation practices. So basically, your soil erosion is function of my rainfall erosivity. That means you can understand that intense rainfalls may erode large amount of soil, because you know that the energy from the raindrop may displace the soil, and similarly if you have short durations high intensity rainfall, it generates quick runoff, which can carry the sediments. Okay, so that is one factor. Second factor is soil erodibility. See, all soils will not erode same amount. If you have cohesion in the soil, then the detachment becomes difficult. So your soil erodibility is the second factor, which determines how much soil is getting eroded. Then slope length and steepness. So if you have steep slopes and longer slopes, erodibility is more. Okay, so that means your erosion is basically based on these three major factors, right? Now, the next factor is crop cover and crop management. Suppose the soil is bare soil, it is open. Okay, then it is prone to erosion. However, if the soil is covered with some crops, okay, that means the raindrop will not directly fall on the ground. Okay, it may strike the crop, so the energy is getting reduced. Therefore, the detachment gets reduced. Okay, and sometimes you may have some conservation practices, that is like you may have some strip cropping, something like that, so that the sediment will not be carried away from the actual land. It may get stopped because the velocity of the flow may get reduced and it can stop. So therefore, your C and P, when the values are 1, means there is no management, no cover, and no conservation practice. The values are less than 1, then there are some crop cover and management or conservation practices are there. So these values, maximum value is 1 for C and P, right? So use these like your erosivity, erodibility, and so you can have 5 different layers indicating each of these values, and then apply a simple map algebra so that you can calculate the average annual soil loss. Okay, now how we can use this? 1 minute, I think. Yeah, land use, land cover change, and flood modeling. Okay, so let us just move on to land use, land cover change, then I'll come back. Okay, so now how this land use, land cover change can be, first of all, why do we actually look for this land use, land cover change? We know that it is dynamic in nature. Second thing is your hydrology is basically your surface water hydrology or groundwater hydrology. It depends on how your land use, land cover is changing over time. So for example, if I keep on urbanizing the watershed, then my surface runoff is going to increase, right? So therefore, I actually need to see that my land use, land cover is not changing drastically, and if at all it changes, how it is going to have the effect on hydrology. Okay, so now you see here, this is as a town like a Tirupati, how the land use, land cover has changed over a period of time. So maybe you can use the old topo sheets or some old satellite images, and you can just compare. You can see that so many water bodies are lost, and then your agricultural fields are converted into, see, this red color is the urban area. Okay, so it is being converted to urban land, and also now currently most of the land surrounding this are open land without any agriculture practices currently. Okay, and also thick forest cover has also come down. Okay, so these are all some things that are going to affect the hydrology. Okay. And again, you can see that mangroves, how there is a change in the mangrove over the years. Okay, so between 92 and 2004, you can use the data sets like IRS data, and you can identify how there is a change in the mangrove. Here you can see. Okay. So these are the some of the studies that will, or some of the things that you can use satellite data and see how it has been changed. And the work is not stopping here. Basically, now what we try to do is, we may try to project the land use land cover for next 20 years or 30 years. Then you apply the climate change into this. Okay, so that you can get to know how your stream flow is going to change in future. So those studies are plentifully available. You can see that many people in our institute, they have published papers using the SWAT model, and just trying to see how the land use land cover is about to change in next 20 years or 30 years, and then how this is going to affect the surface water hydrology. Okay, so now moving on for floodplain modeling. So you can see here, as I already mentioned, this DTM is required when we are looking for this floodplain modeling, and you may need a stream network, land use and soil map. Okay, and the discharge data. So basically what we have seen here. Okay, so the same thing, you can understand this is used for flood model. I already shown you how HMS is being used. So if after HMS, okay, you have the discharge data, and you can use this HECRAS model. Okay, and you can get the 2D flood model, that is, you can get the velocities and depths. Okay, and actually this will be used for, you can check whether your model is correct, and then after that you can prepare the flood hazard map. So basically, coming here, there are different types of flood models. Okay, either you can use 1D model. So here what I have shown here is, this is 1D. Okay, so HECRAS, earlier you had only 1D model, but now we have 2D models. So where this entire floodplain is divided into two-dimensional grid cells. Okay, and for each grid cell, I can get the flood depth and as well as velocity. Okay, and again, this is something like unstructured mesh that you can create, and certain models can work on this unstructured meshes. Okay, so this is very commonly used, like structured gridded cells, and we try to get the floodplain inundation, so that we prepare the flood hazard, flood risk, okay, and flood vulnerability. Right. So you can just browse this website, that is USGIS flood inundation mapper. So where you can get the for any specific river, you can get the water depth, that is for any location, what will be the water depth for a particular they will be just providing you the real time data set, that is expected water depth and discharge, etc. You can see here for any location that can be obtained. So this is basically a web-based platform, okay, using GIS and other flood inundation or flood simulation tools. They just try to get these results. Okay. Okay, now moving on to groundwater modeling. See here, we can use groundwater models may require some lithology that has to be given in the GIS format. That is one thing. But here I am trying to just give some glimpse of a model which is basically uses the maximum potential of GIS. Okay, so this is called as drastic model. Okay, and it is used for pollution hazard assessment. So the drastic, it is derived from the first letter of these. You can see here. Just look at the first letter. DRASTIC. Okay, so basically it uses this 7 data sets, that is depth to the water table, net recharge, so recharge, that is net, aquifer media, that is geological characteristics, soil media, topography, impact of water zone, that is unsaturated zone above the water table, then hydraulic conductivity. Okay, so C, conductivity. Now, if you see here, see, as I already mentioned, you have these 7 different layers, GIS layers. Okay, and what you do is you give this rating for each range. That is, for example, my groundwater depth is